All right, we are now recording. My name is Lady Leonor da Costa. A couple quick housekeeping things before we get started. First of all, we are recording, so your continued participation implies your consent. And if you do not want your face on the recording, please turn your camera off. And at this point, please put your name in the chat if you want credit for it on University of Atlantia, and I will mark you here. All right, let's get started. So our class today is African mathematics, and we're going to be looking at a kind of an overview of some of the mathematics technologies that exist in Africa. I am Lady Leonor da Costa. I'm from the Barony of Cairta in the Kingdom of the Outlands. I am currently the Kingdom DEIB Deputy over the Barony of Cairta. And this is the event that I stewarded, Mansa Musa themed. Mundanely, I have a master's degree in mathematics and I teach. I am currently teaching middle school science, but I have taught college and high school as well. So here's what we're going to be learning today. We're going to learn a little bit about mathematics pre-1600 on the continent of Africa. This is a large continent. There is a wide variety of mathematics, cultures, things like that. But we're also going to kind of learn a little more about how non-Western mathematics styles look and feel. And we're going to learn about how sand divination, there's like a trail of connections there to the modern computer. So we're going to learn about that. So our Western mathematics is, we often view it as like there's these universal truths out there, and they are all there is to mathematics, and everybody just discovers these there's kind of this like Platonic heaven thing going on, and then we focus a lot also on like solving equations. One of the big things I have to disabuse my students of is that when you go to college and study mathematics, you just solve bigger and bigger and bigger equations. That is not how it works. After a certain point, you start proving things and you don't solve much of anything. You just do a lot of proofs. And, you know, you get to graduate school and it's like all proofs. Everything is proofs. So, but this idea that we have is pretty cemented in our culture, that this is some universal truth, that if everybody doesn't have it the same way, they just haven't discovered it, that everybody's going to discover this stuff in the same way, and if they haven't, they're not advanced enough. Wow, how Victorian and colonization type orientation. Okay, these are not the only possible views of mathematics. First thing to understand is that mathematics is a technology. It develops in feedback with other technologies. So like if you have, science and math, for example, in the West develop together. Science usually picks up math about 100 to 200 years after it's been discovered, although that's not a universal limit. Like Dijkstra is still alive and his algorithm is being used in Google Maps. So, it's not always the case that, math or science lags that far behind mathematics, but they do develop in sync with each other. Sometimes people will develop the mathematics they need for the science. Sometimes they develop the science to fit the mathematics. But more importantly, mathematics develops to meet cultural needs. Whatever a culture values, that's what their math is going to be oriented towards. When they have traditions, their math is not going to allow them to step outside those traditions, which is kind of interesting because we like to think of math as completely independent from any of that, but it's definitely not. And it's not a set of universal truths that everybody just discovers in the same way. Now, many cultures come to similar conclusions because there are certain things that end up being facts. Like pretty much every culture in the world has discovered that like 1 + 1 is 2. Some of them, most of them, have discovered that 2 + 2 is 4. Okay, there are cultures whose number systems do not go beyond 2. Very rare, though. So when we study African mathematics, we are going to be forced to reconsider what we mean when we say mathematics. It's systematic thinking about quantity, shape, and relationship. And this rethink is actually happening in our modern mathematics, like when we do curriculum and standards. Those are actually being more considered than just techniques and solving equations and particular mathematical procedures. So we're starting to shift the thinking on that in the education part of mathematics. It still has not shifted in the general popular culture. But it is thinking systematically about quantity, shape, and relationship. So we are just now in Western culture gaining the tools that we need to understand how African cultures, or some African cultures, view the relationships between quantity, shape, and thought. What they produce is not going to resemble necessarily what the ancient Greeks have. And it's not going to necessarily resemble like the algebra of medieval Arabia or anything like that. It's going to look differently. Mathematics looks differently in different parts of the world. I actually taught a class on this to other teachers. It was an ethnomathematics class, and it was very interesting. I don't like the term ethnomathematics because it implies that there's like real mathematics and ethnomathematics. Ooh, it's spicy. But I mean, it's all just mathematics, but that's the term of art that you use to go do the searches. So, pop quiz. Now, I'm not going to make you do any math problems. I like to aim my basic mathematics classes towards people who really are not interested in solving equations like they did in high school. But I do have a pop quiz question for you. Which area of the world has the oldest evidence of mathematics? Is it A, Mesopotamia, B, China, C, Egypt, or D, Sub-Saharan Africa? What do you think? Put it in the chat. I see a C, an A, a D, an A, a B, a D, an A. All right. You ready for the answer? It's D, Sub-Saharan Africa. Now, when I say evidence of mathematics, what am I thinking of? I'm not thinking about like we found that they were solving quadratic equations. I'm thinking like we know that they're thinking about the relationships, quantity, number, things like that, and able to do like operations and things like that. But the oldest evidence that people were thinking about that is actually the Ishango bone. It's 20,000 years old. Now, there is an older bone that's about 40,000 years old called the Lubumbo bone, but we don't have any evidence that suggests that it was more than a tally stick. It is still evidence that people were thinking about quantity, but this is the first one that shows evidence that they're thinking about the relationships between quantities. There's varying numbers of marks in different parts of the bone, and these marks add up to either 48 or 60 on alternate parts of the bone. So there's something going on there that shows that they are they're actually thinking about what the relationships are between these quantities. It also contains a lot of prime numbers, although it would be a stretch to say that this is supposed to be a list of prime numbers. or that they understood prime numbers as prime numbers, because that's the way that we understand prime numbers, but that's not necessarily the way that somebody else might understand it. And there are also composite numbers on there, so it's not strictly speaking a list of prime numbers. But it is evidence that people were thinking about quantity in relationship 20,000 years ago in the Congo. So we have a couple different things coming up for us today now that we've had a little introduction. The first is I'm going to talk about mathematics in ancient Egypt, because that is kind of the foundation of a lot of the stuff that we do today. The other foundation being Mesopotamian mathematics, which I had another class on that, ancient mathematics, that goes into mathematics in a bunch of different ancient cultures. So if you have taken that class, this next section is going to be familiar to you. I also have a section on the way that sub-Saharan mathematics is. It's very different from Western mathematics, and you're going to see that. And then I have a section on the connection to computing. So let's talk about ancient Egyptian mathematics. We got a little bit of a timeline. We are talking about a large stretch of time. Like we're talking thousands of years here between the earliest evidence of numeration and the like the Rhind mathematical papyrus. They went through many, many changes of dynasty and things like that. But here's kind of a basic timeline. The earliest evidence we have of numeration, that numeration is like writing down numbers with symbols. The earliest evidence in Egypt we have of that is 3200 BC. That's before the pyramids. That's about almost 1,000 years before the pyramids. So they had some time to develop some math. We've seen some inscriptions that have guidelines for slopes of pyramid sides. This is basically your manual, for your architectural manual, how you design one of these pyramids. That's about 2500 BC. We have papyri dating back to about like maybe 2000 BC-ish. Papyrus is really perishable, and it's hard to preserve it. And so it's rare that these would be preserved from even that period, let alone before then. So the capabilities that they had in ancient Egypt, especially towards the end, we have evidence for. They may have had these capabilities before this, but this is when we have evidence for it. That they could do arithmetic. That would include fractions, linear and quadratic equations, areas and volumes, and slope. They could do that. They could calculate slope, although they calculate it a little differently than we do. And when I say arithmetic, I mean your addition, subtraction, multiplication, division. Fractions, the Egyptian fraction system was actually the world standard for a long, long time, like thousands of years. Egyptian fractions are a little different. They all have 1 as the numerator. In fact, today, any fraction with a 1 as the numerator is called an Egyptian fraction. The only exception was they had one for 2/3. They had a different symbol for 2/3. It's kind of an interesting fraction system. It is hugely kludgy, though, and it relies on tables. Here's some of the more famous papyri that they have from ancient Egypt. We have the Moscow mathematical papyrus. We have the Rhind mathematical papyrus. These are textbooks. These are math textbooks that have problems and solutions to teach people how to do the math. So they can teach us how ancient Egyptian scribes would also do that math. So the Moscow papyrus is a problem book. It has algebra, geometry, and ratio problems. The Rhind mathematical papyrus has some of the same, including fraction problems. It has fraction tables and partial sums of a geometric sequence, which is kind of an interesting thing to have in your mathematical corpus. I think I've frozen. My computer froze.
We're still hearing you.
Oh, okay. Well, then
Yeah,
I'll
we can
keep
still hear
going.
you. I think it's your camera.
Okay, just my camera froze. My mouse is not moving either, so that's going to be kind of interesting. The Berlin Papyrus has the earliest known solutions to quadratic equations. So it's kind of interesting.
You dropped out.
Leonora, can you hear us? We can't hear you. There is no TI that I know of, but I will try to message her outside and get her to restart.
My computer is blue screened, so okay, here it goes. Let's get it back up. But I'm sorry about that. This is a new computer for me, and it belongs to my work. All right, we're just waiting for Chrome to restart. PowerPoint restarted already. I'm sorry about that, everyone. All right, I think we're back.
We can hear you again.
Okay.
Yeah, I can hear you and your camera's not frozen.
Okay. I think I am going to stop my camera, though, because I'm not sure if that will affect the ability of my computer to run this. All right. So the numeration system that Egyptians used, because remember, math is a technology, numeration systems really do affect the ability that your culture has to perform mathematical stuff, because certain operations are better in certain numeration systems, and others are better in others. The one we have right now is really powerful in our culture, the one we have, but this was what they had in ancient Egypt. So what they've got is a non-positional numeration system, meaning that like there's no such thing as a 2 that can mean 2 or 20 or 200. If you want 2, you write 2 little lines. And in fact, the little line, I just made a gesture and forgot you can't see me. The little line like this is, it's a very almost universal symbol for the number 1. But the way that the Egyptians did it was, if you wanted more than one of those, you would put more than 1. And if you meant 10, you would put this little kind of inverted U shape, which is a hobble. And then 100s are represented by coils of rope. 1,000s by a lily pad, 10,000s by a finger, 100,000s by a tadpole, and 1,000,000 by a guy with his arms up going, oh my gosh, that's a big number. So that's what their numeration system is. It's non-positional. The order in which you put the symbols does not matter to the final number. They also had the ability to do multiplication by an algorithm that we do not use today, but it's quite an interesting algorithm, and it might be a good alternative for kids who have learning differences. Egyptians also had some practical geometry, which I distinguish from theoretical geometry. Theoretical geometry is like your Greek style, proof style geometry. If you've ever been subjected to doing a 2-column proof, you have done Greek geometry. But most other cultures in the world do not concern themselves with proofs in geometry. They're mostly concerned with, can they get results out of their geometry? So this is what I call practical geometry. And they had the concept of a slope of a side of a pyramid. Theirs is the reciprocal of our slope, which a lot of my students think is the slope formula. That's a very common mistake. But they do run over rise instead of rise over 1. And it's also equivalent to the cotangent of an angle. But we're not certain what their trigonometric knowledge was. There's not been evidence of that so much in the... I have a question, powers of 10, which cultures have anything other than 10? That is a really good question. There are a few that have base 8 because there's 8 spaces in between your fingers. So they would count objects by putting them between their fingers, and that gives them a base 8 system. The most notable alternative base systems are in Mesopotamia, where it's base 60, and in Mesoamerica, where it's base 20. So base 10 is not universal, but I do have that in another class. I do address that in a different class. So what I would like to talk about now is what we kind of mathematics we see in sub-Saharan Africa, what kind of things that we see there. And to understand it, because it's highly geometric, we have to understand fractals. So for those of you who are not familiar with fractals, I'm going to give a little primer, because a lot of people aren't familiar with them, but then they kind of are. So a fractal is a shape that's self-similar. It's going to look the same at different levels of magnification. It's going to be iterated. That means it can be generated using a rule. I like to freak out my students sometimes when I'm teaching fractals with, you ever seen these finger hands? They're little hands that are like finger puppets of hands that go on your fingers. So I put one on each finger, and they get really freaked out because it's really uncanny that there's like there's like a hand on your hand. But that's a rule that you have. On every finger, put a hand, and then on every finger of those, put another hand. Fractals also have fractional dimension, and this is some higher math stuff. I'm not going to get into exactly how we calculate it, but it's basically like a straight line is one-dimensional and a plane is two-dimensional, but anything that's in between that's not quite a straight line, it's more than a straight line, but it's not quite an entire plane, that's going to have a fractional dimension between 1 and 2. So let's take a look at some familiar fractals that we see all the time. On the left, you see broccoli. So broccoli is fractal in structure. You may have noticed that if you cut off a floret of broccoli, it has the same kind of structure as an entire head of broccoli. And then if you cut that further, you can subdivide it further. That's that self-similarity on different levels of magnification. That's that iterative generation. And then over on the right, we have some fossils of different sizes of, I can't remember, are they ammonites? I can't remember. They are different sizes, but they're the same shape. And a lot of shells take this kind of form where they're self-similar because of the way that the animals grow the shells. But I wanted to show the broccoli because it's familiar, but the shells because the shell thing where there's different levels of magnification in different spots, this is more like the fractals that we see in African mathematics. So there's a really great TED Talk on this. Ron Eglash, I'm a Ron Eglash fangirl, but he's got a really good video on it. He's done a lot of research on it. This is a Baila village in Zambia, and it's laid out in a fractal pattern. So he shows the fractal generator, that's figure 1 down at the bottom, that he used to generate basically the village. Yeah, I have a bibliography at the end, but it's if you search up Ron Eglash African fractals on YouTube, that will show you the TED Talk, and he talks in more depth than I'm going to go into here about fractals. But the basic idea is that the village is laid out in a ring, and every family grouping has a ring, a sub ring, and then every family in that grouping has a sub ring. And at the center, or well, not the exact center, but like in the middle, there's an altar, or like a common fire where the ancestors are worshipped. And there's a little ring in the center of the village that's for the ancestors, and they have their sacred fire. Sorry, this is the chief's residence. Sorry, and then at the very center is the ancestors. So it's kind of interesting because this reflects their social structure as well. It's not just their like this is a cool way to lay out a village. This is also reflecting their social structure, where they have kind of a like the chief is in charge, but the chief worships the ancestors, and then the family groups respect the chief, and then within the family groups, the families respect the head of the family group. It's a fractal structure. It is self-similar on multiple levels, and it makes it interesting because think about just for a minute how you would assign zip codes in a village or addresses in a village like this. Like it's non-linear. It's not Euclidean like we have, zip codes and addresses and things like that. So they're actually looking into using fractals to generate addresses. It's kind of interesting. Here's an Ethiopian cross, and you can see that it is generated using 3 iterations, specifically 3. The Ethiopian crosses are generated with specifically 3 iterations used from a starting shape, and they use a rule to expand it. So let me explain how that works. You take this starting shape, this like diamond with the little nibs on the corners. You make 4 of them, okay, and then you put a small one at the junctures. And then you take that and you take 4 of them and you put them together into a cross, and you put little ones at the junctures. And that's going to generate for you the complexity of an Ethiopian cross. There's a number of different ones but you can tell that they are all generated from it, and they're all iterated in 3 iterations specifically from a particular starting shape. It's really interesting. Here is a Fulani wedding blanket with comparison to the Cantor set, which is a very famous, highly mathematical fractal where you start with this one bar on the right, and you take its middle third out, and then each of these bars that's left, you take its middle third out. Each of these bars that's left, you take its middle third out, and you keep going until forever, until you decide to quit. But if you look at the structure of the blanket, you can see that here's a diagram on the bottom left of the structure of the design, and it does have a fractal feel to it. You are getting self-similarity at different levels of magnification, so it does have a fractal structure. Interesting fact about these blankets, they have to be woven in one sitting. Like the weavers will just work and work and work. People will bring them food and things. They have to work in one sitting until they finish the wedding blanket. So now here's the part that you've all been waiting for, the sand divination. So the Bamana people of Western Africa, they practice divination, which for those who are not familiar with what that means, is like fortune telling. Think of like tarot cards or things like that. The way that they do it is they use randomly generated lines drawn in the sand by a moving finger. So you just kind of dot, 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 not even thinking about anything but your question. So then they run the patterns of lines through an iterative process and they obtain the result. And when I say iterative, I mean it goes in multiple steps. You do the same kind of thing in multiple steps. That's what iterative means. It means you're doing it over and over. Now, Bamana sand divination exact practices, I don't know, and I don't have access to them. They are sacred, so I'm not going to pry, but in order to be initiated into their practice, you have to be a heterosexual male, which I am not male. So so that's off limits to me, but I do have access to what happened after that. This practice spread to the Middle East through the propagation of Islam to Africa. And then from there it spread to Europe. And in Europe, it's called geomancy. So this is how it works, okay? You're going to make 12 lines of dots. Right here, the dots are paired up. So that when you have two dots with a line through them, that means they're paired up. There's two dots, and they've paired them up because you're going to count whether the number of dots is odd or even. Not how many there are, just whether they're odd or even. So you can see that on this top line, we've got pair, 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 pair. That's an even number. So we're going to interpret that as this top line of the figures on the left, that we're going to put 2 dots. We're going to reduce any even number down to 2 dots. We're going to reduce any odd number down to 1 dot. So we've got pair on the second line, pair, 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 1. So that's going to be an odd number, and that's going to give us the 1 dot here. And so if you keep going through this process with your 12 lines, you're going to, 16 lines, you're going to generate 4 figures. 4 different figures with 4 dots each. There is a superficial resemblance to the I Ching here. It is not, as far as we know, there's no connection. It's just a shared technology. People came up with the same technology, similar technology for fortune telling. I Ching, if I remember correctly, depends on euro stocks. They cast euro stocks a certain way, and short ones and long ones. So once you have those 4 figures, those are called the mothers. And we work right to left for this instead of left to right, like traditional European writing. So then you're going to combine the mothers to generate 4 daughters. So you're going to take the first line of each of the mothers, going right to left. So this is 2 dots, 1 dot, 1 dot, 2 dots. And that's going to generate the first daughter, which is over here, 2, 1, 1, 2. Okay, so those are the daughters. You generate the daughters using the mothers. And then you pairwise add daughters and mothers to get the nieces. So when you add this one on the left to the next one next to it, you get this one, that's the niece. You add these 2 together, you get that niece. You add these 2 mothers together, you get that niece. You add these 2 mothers together, you get that niece. So then you get the nieces. And then the witnesses are made by pairwise adding the nieces, and then the judge is gotten by pairwise adding the witnesses. And then finally, to complete it, you add the judge to the first mother, and that gives you the reconciler. This particular formation is called Fortuna Major, Great Fortune. I have a table in the slides of all the different figures. But that's how you do geomancy. So the interesting thing about it is that it basically includes binary addition, which is not something that people who are used to a base 10 system, I mean, we can kind of intuitively grasp it because we have computers. We're in the age of computers, but it's still like kind of foreign. Like the idea that you would add 2 numbers and there's only 2 numbers in the world, 1 and 2 or 1 and 0. and you can just add these numbers all up. It's kind of whack, for lack of a better word. It's but it's the foundation of modern computing. So here's how we make the connection. Okay. So binary addition. Okay. Gottfried Wilhelm von Leibniz, yeah, that guy, the one that got in the fight with Sir Isaac Newton about calculus invention. He also proposed a formal system of binary numeration in 1703. His inspiration was the I Ching. However, he was also, geomancy was current at that time, so it could be something that was kind of floating around in the cultural ether that he had kind of thought about, or he knew about. There's not a documented link between those two or between Leibniz and that, but it was kind of in the air at the time. But the binary arithmetic inspired George Boole, he of the Boolean logic, Claude Shannon, all the other, what would you call them? Like the pioneers of computer science. Okay, so binary addition is very closely related to Boolean logic. So when you add the different operations are like different operators, like and or. It's kind of interesting, the connection there. I'm not sure if I'll have time to go through that, or if you have the interest in it. Thank you, Jennifer Whiteside, for posting the link to the African Fractals video. I should also post the link to the the folder. I have a folder where I've put some other interesting articles. Give me a second. I'll copy that link. Here's the link. So this is the link to my class folder. The video will appear there after I am done. The handouts are there, the slides are there, and also some articles that I found interesting, most of them from Ron Eglash, but also some others. And if I find other interesting things, I'll upload them there too. Questions? It's time for questions.
Yeah, so this is Thomas, or Brandon Dupree, mundane name Brandon Dupree. Is there any compilations or any professors that have like active working knowledge of how to use these systems to solve mathematical problems? I'm just asking this because like my persona is like I guess a medieval engineer, what you would call it, and I'm very interested in solving problems in the way that you would approach it given the time period. So like no Newtonian mechanics, no what you would think of in the modern engineering education. So is there something like that around?
Yeah, so at that, any particular place in that time frame, or all places in that time frame?
At this point, I'm just casting a wide net and then just sort of following that rabbit hole.
Okay, because European people would not have had access to some of the other techniques that I'm about to describe. I do have a class called Here's Looking at Euclid that's on video, and it's on YouTube somewhere. And it covers like the practical geometry, some of the practical geometry. But like the Mayas, for example, used geometric construction, what we would call geometric construction, to lay out their houses in particular proportions. The Chinese were super engineers, because remember, these people were building dams and things like that, and the Great Wall of China speaks for itself. They have a lot of engineering savvy, but they're not real concerned with like what Western mathematics being concerned with proof. They don't care much about proof. They want results. I have a question in the chat. Could you say more about how the original groups of numbers were generated in the sand divination? So basically, I'm going to turn my camera on so you can see what I'm poking at. So you would make dots, dot, 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 just with your finger. While you're thinking about the topic that you want the reading on, you'll just make dots in the sand in a line, just random number of dots. And then you just keep making those until you have 16 lines. Does that help? Yeah, it's not deterministic. At least the inputs aren't. The iterative process is, but the inputs are random. And you could easily use like a random number generator if you wanted to generate a random binary string, interpreting 0 as 2 rather than 0. If you wanted to practice it. In the slides, I have a list of the geomantic figures. And you can find them. There's a link in the bibliography on the slides that that goes to, like, walks you through the process and what it means, what each of these figures mean. Questions?
How much did the different societies interact and exchange, or, like, I guess maybe when did they exchange? You know anything about the exchange?
That's a really good question. This kind of technology tends to go through trade routes. It tends to pass through trade routes because what'll happen is somebody will visit a foreign country and they'll say, "Ooh, they have this really cool thing here," and they'll tell the king or whatever, and he'll be like, "Bring me someone who can make me one." So they go back, they get somebody with that technology, and that's how it spreads through cultures. You're looking for a good book for sub-Saharan mathematics. I am still working on expanding my my stuff on that. It's hard to get, but I do have in my bibliography, I've got the Africa Counts, this last one. I have a copy of it here. Hang on. You can see what it looks like. This is what it looks like. Hold that up to the camera. It's hard for the camera to think about it, but number and pattern in African cultures, that's a classic, but there's really not a whole lot of work on this that's published in books. You can get articles that people have done, and Ron Eglash in particular. Like, I'm a Ron Eglash fangirl, and Ron Eglash is like an African fractal fanboy. So he's got a lot of stuff on the fractal aspect of mathematics in Africa. And most cultures will have basic 4-function operations. They usually, at least the first 3, they have addition, subtraction, and multiplication, because they got to do stuff. You know, they got to do trade. They got to build things. They usually have some kind of practical geometry if they've got civilization. But as far as, like, you know, solving equations, that's not necessarily everybody's priority. And some of these technologies are more like traditions that develop over time. Like, of course, you would structure a village this way. Of course, you would make a braided windscreen this way. One of the things that Ron Eglash has in his TED Talk is he talks about the fractal weaving of the windscreen fences, and they have like it matches up exactly, almost exactly to like wind speed based on altitude kind of things. It's really cool. You got to see the video, but yeah, there's a lot of different articles out there, but not many books. Questions? Okay, while we're waiting for any more questions, if you wouldn't mind dropping your SCA name in the chat for attendance, if you would like to be counted for purposes of University of Atlantia after class, I will enter the roll and you will get credit for it. I think the recording didn't stop while I was out, which is nice, but just in case it did, you might want to drop it again if you dropped it earlier. Any other questions?
Not so much as a question as, oh, girl, this class has been fascinating. I can't wait to go check out about geomancy. So yeah, just more of a comment. Thank you. I am so excited. This has been amazing.
Thank you. I'm glad you liked it. I do have other classes that I've taught before that are on YouTube. So here's looking at Euclid is geometry pre-1600. I have intro to medieval mathematics or overview of medieval mathematics. I have ancient mathematics 1 and 2. I did not get a recording of, but I do have a class I can teach on the geometry of the Alhambra. I found the Euclid class. Thank you. Yeah, it's not original though. I've got it from some book or other, but yeah, it's not an original name. Years looking at Euclid. And I'm always exploring more. So if you find any resources or anything like that, please pass them along. And they will inform future classes. I am continuing my research, although it's kind of been paused because I had some changes in my life happen. I had to change jobs, and there was a lot of other things that changed at the same time. So,
I guess not a question, but just sort of I guess what if. So me and a couple other guys here were also interested in astronomy, and so we're guessing, would you know any resources of like how they use mathematics for astronomy in, like for example, Africa or Mesopotamia or Mesoamerica?
That's a hole in my knowledge. There's because I'm a pure mathematician, so like I'm not up on all of the applications of the applied math. I do know that if you're interested in the connection between astronomy and mathematics, you might want to look at Mesoamerican astronomy, which is it's fascinating how that interacts with their math. They have a base 20 system, but they had like a second version of it that has an 18 as the second column. So your second column ticks over at 18 instead of 20, but all the rest are 20. And that allows you to do computations based on 360, which is close to the number of years or days in the year. So that's kind of an interesting factoid there. That might be something you could look into. Owen asks, is there an interkingdom guild or anything that works on period science and math? Not as far as I know. I'm sure there's probably one for science, but I don't think there's one for math. I'm not, if there is, please pass it along because that would be an interesting thing for me to join. And I have never been to Pensick. I would love to go, but I am a teacher and I'm often required to return to work at the same time as Pensick. So. Thank you for dropping the link to the overview of medieval mathematics. I also do cooking classes, and I just recently did one on inclusive feasts. At my event, we had our feast as kind of like food stalls, like you would be in the market and there's food stalls. And we gave everybody at gate 30 cowrie shells, and you could go to oh, you saw the almond cookies, nice. Yeah, there's one you can go to, or you could go there and get like a whole meal for 15 cowrie shells or a snack for 5. And that way you could try like every single one and get enough for a meal. That was Kirk the 12th night, the Hajj of Mansa Musa. We just recently had it back in January. And if anybody wants to do a similar event, I'd be happy to share my notes. All right, it's 11:50. It's time to release you all to your next class. I appreciate you coming. Thank you so much.
Thank you.
Thank you. Great class. And I'll see you at the end of class today on FB.
Thank you.